Hey, good. So here I'm showing a plot of with 7 spectra of the main sequence of 47 TOC. Here the arrows, with the arrows I'm showing you a molecular band that is a proxy of nitrogen abundance. In yellow, I'm showing you a cluster star with normal nitrogen abundance, and in blue, I'm showing you one that is nitrogen rich. The difference between the two stars can be seen in the lower right panel, in the lower right spectrum. So what does this mean? So this means that it cannot be an evolutionary effect. As abundances, these abundance variations are already present in unevolved stars, okay? In other words, the abundance patterns must be present in the material where globular clusters form. This is why understanding the origin of these abundance variations became a synonym for understanding globular cluster formation. So let me go now briefly over the main pieces of evidence, okay, that make this big mystery. So, okay. So here I show you a plot of the abundances of some light elements that change the most between stars and globular clusters. I'm going to go over this in detail later, but for now, what you need to know is that a tiny fraction of the stars have the same abundances as halo stars of the same metallicity, but most of the cluster stars have a very anomalous chemistry, okay? They are enhanced and depleted in some elements. I'm going to tell you later about that, okay? Again, very few stars in the field show these chemical patterns, and they are completely consistent with the numbers that we expect from stars that were lost by globular clusters, okay, during their evolution. Okay, also, the abundance variations are not random. You can see here in this plot that they follow very specific correlations and anti-correlations with each other, okay? And they also follow very specific elements that I'm going to tell you later, okay? And okay, good. So some abundance variations are so severe, like in nitrogen and helium, that they can be cut by broadband colors. So here in the right, I'm showing you a CMD that instead of having one color in the x-axis, it is using a combination of two colors, okay? In this case, U minus B and B minus I. This allows a better separation between stars with different chemistry. You can see that the stars in black are segregated to the left, while the stars in blue and red are segregated to the right, okay? This is basically the same trick that we're doing with a spectra, okay? But now we can do it with colors. So the abundance variations are ubiquitous to all globular clusters, right? That has been studied in enough detail using spectroscopic and photometric surveys with techniques like I'm showing you here. This not only includes stars in the galaxy, globular clusters in the galaxy, but this has also been found in M31 and the NMC, SMC, Sagittarius, Fornax, and WLN. So these are basically the nearby galaxies where we can resolve some of these individual stars. Okay, another thing that you need to know is that in these abundance planes, as you can see here in this example, the abundances seem to follow a continuous distribution, okay? And you can get the same when you do the CMD that I showed you before. However, this is where HST revolutionized the field. So with this incredible precision, we can split superpopulations with extreme efficacy, revealing discrete groups of stars with different chemistry. So you can see here that, for example, in this CMD on the right, focus on the main panel, you can see that multiple sequences, I don't know if you can see my mouse, no. Okay, so you can see multiple sequences in the red giant branch and also in the main sequence, okay? So like we said before, we can trace, yes.
Just to let you know, we do see your cursor. So if it helps you to point out things, that works.
Yeah, I also see it as well.
I don't see it here, but I don't see it, that's a problem. Well
Well then, never mind that.
Yeah. Okay, sorry about that. Okay, what was I saying? Yeah, so we can trace this across all evolutionary stages, okay? Like we said before, we see it in unevolved stars as well as evolved giants. And another good thing about HST is that now we can study an unprecedented number of clusters. This was an improvement of factor of 3 from any previous studies. So it is an instrument that is essential to our field. So since I'm going to be showing you a couple of results based on this, it's a little bit, it will be good if we understand how this magic works. So here in the top panel, I'm showing you model spectra of 2 model stars with globular clusters chemistry, right? One has the normal abundances, which is the red one, and the blue one has the anomalous abundance patterns that we see in globular clusters. In the middle panel, you see the difference between the two, okay? And you can see that that these differences are so severe that we can pick them up with some of these photometric filters, like in the UV and the U mostly, okay? So let's summarize what we have so far, what we have learned so far. So one, most of the stars in globular clusters have anomalous chemical compositions. These are not found in open clusters, nor in stars in the halo of the similar metallicity. They are present in all evolutionary stages, in the unevolved stars as well as in evolved stars. So this suggests that this related to star formation processes of globular cluster formation, and that the abundance variations are not random. They follow specific elements and follow very specific patterns of correlations and anti-correlations with each other. So let me tell you a little bit more about this now. So the chemical signatures are, we can boil it down in these two. So we see an enhancement in helium, nitrogen, sodium, and aluminum. And in the same stars that we see this enhanced, we see them depleted in carbon, oxygen, and magnesium, okay? So this is what you get essentially when you burn in high temperature hydrogen, okay? So through the CNO cycle. So these abundance patterns come naturally from this. So the models were built from this assumption, that all the models I'm going to show you later, okay? So one question we often get is, what about supernova? Can supernova get some of these abundance patterns? The problem with supernova is that in globular clusters, we don't see iron spreads or iron peaks abundance variations. So it's not like galactic chemical evolution that we see an enrichment, okay, of metallicity as well. So there are a few exceptions of very massive globular clusters that have some iron spreads, but there's a consensus in the community that those are strange beasts. So I'm not going to be talking about those today. Okay, so let me go over the models. So this bit from Graton's review a few years ago summarizes the logical argument that was used to build all models that we have today, okay? We can break it down in 3 chunks. So first, the abundance patterns are the product of hot CNO burning, okay, because of the signatures that we saw earlier. But since globular cluster stars are very low mass, they don't have the temperatures inside to burn these reactions, okay? So the idea is that these abundance variations came from a previous generation of stars that are more massive, so they have hotter interiors that were able to produce this. So it's a simple self-enrichment, where massive stars produce the chemical anomalies that eventually are going to be ejected into the interstellar medium by winds, and this is going to form a new generation of stars. So these are like the same 3 steps that I showed you before. And the only difference, or the main difference between the models, is the source that is produced in the hot CNO, okay? So there are different ideas that has been proposed to explain this. But basically, there are massive stars, okay? That they are the ones that can burn this in the interiors. And your choice of star is going to set the time when the time scale where star formation takes place. Some are longer than others, but basically we're talking about approximately a few 100 million years between the star formation of the normal stars and the star formation of the stars with the funny abundance patterns. The thing that most of them, of these models, were mutually exclusive. So figuring out which one was working or which one was right was a priority in the field. So this is what I've been studying in the last few years, trying to go through all these steps and try to produce evidence to support or refute the different models. Okay, so let me start with the first premise, okay? So the different, the chemical signatures that we see or that translate into the different photometric groups are a reflect of the product of hot CNO burning, okay? So using HST, you can create this fancy color plot that is a very good at separating stars with different chemical signature. For example, in this figure, each color represents a unique chemical pattern. So I'm going to use this to show you how this fundamental premise of the hot CNO burning as the source of this material breaks down. So let me tell you what you're seeing in this plot. Okay, so in this plane, you have that nitrogen increases upwards. You can see it in the brown and orange boxes on the left, while helium increases to the left. You see that the darker shades of blue are more helium-rich stars, or stars that have more helium than the others. So from here, you can see, for example, that the stars that have the highest helium enrichment also have the highest enrichment in nitrogen, which are the dark blue and the dark brown colors. However, we notice something strange, all right? You see that, for example, that here in this, in the bottom, you have stars with constant nitrogen abundances, but they seem to have very different abundances of helium. And the reason is that this is weird is that the CNO processed material changes nitrogen in lockstep with helium, okay? So if helium is changing, nitrogen should be doing the same. So this is what some models are telling us. So what I decided to do was just to go out and get some spectra and actually measure this, okay? To see if we were getting the right picture from these models. So here, I'm showing you the same fancy color plot as before that separates stars with different chemistry. Here you have stars with normal helium abundances. And here in this group B, you have stars with helium that is enhanced with respect to the normal value. So when you get the spectra of these two stars and measure the abundances, you get that they are all homogeneous in carbon, nitrogen, oxygen, etc. Okay? Remember, the premise is that the hot CNO cycle is responsible for these abundance variations. And when you change helium, nitrogen, carbon, and oxygen should change as well in lockstep. But this is not what we see here. Stars with different helium are homogeneous in carbon, nitrogen, and oxygen. This is not what you get from this hot CNO cycle. In fact, this looks more what you get from PP chain, all right? So we need to see how to fold this into the models. But the bottom line is that the basic idea that all models are based from, it's flawed, or at least incomplete. So we see helium changing, but CNO abundances remain constant. So there are other problems with this premise, okay? But they are a little bit more detailed. And I don't have time to go over this because I need to go over different lines of evidence. But I'm happy to talk about those later if you are interested. So let's go over the second point. So after you have your massive star, you picture some winds that are going to be sinking into the stellar winds that are going to be sinking into the cluster center. So you're going to have a gas reservoir where you're going to form stars with the phony chemistry, which is the next step. Okay, so I'm going to test whether or not we see these gas reservoirs within the clusters. So this is pretty straightforward. So you could do this by looking at the global clusters forming today. So for this, we will need young globular clusters. In the local universe, we call them young massive clusters or superstar clusters because of their mass. Although they are pretty rare in the Milky Way, we don't need to go too far to find them. For example, you can see them in the Magellanic Clouds forming today. These two clusters I'm showing here have the same mass and size. The only difference is that one is 10 million years and the other one is 10 gigayears. And the majority of models don't care if the globular clusters are forming today in the Magellanic Clouds or if they formed 13 gigayears ago at high redshift. So what we did was to look at the gas content and these young clusters at the exact time. The models predict we should see these reservoirs that are going to form a second generation of stars. So the timescale changes from model to model, but basically we're talking about a few 100 million years. So of the molecular gas, and you can see that in the clusters we don't see any gas. So when you see the spectra, it's just noise. And the upper limit that we can place with this is below the predictions from the most models, okay? So you can do the same trick with H1 and also with the dust emission, and you get the same answer. But funny enough, it turns out we can place the strongest constraints using gas reservoirs or on the presence of gas reservoirs using photometry by measuring dust extinction. Okay, so here, Steve Longmore used the gas profile of some of these hydro simulation models to calculate the extinction profile expected for a young globular cluster that is going to form a second generation star. So we will expect very, very severe extinctions in the center of these massive clusters, but that's not what we see. In most clusters, they have relatively low extinction, okay? So he had this very funny cartoon. So this is something that you expect. So in the very core of the clusters, you expect them to see them severely extinguished, but we can rule out this by looking at the cores of the clusters within the integrated light, all right? And this is not what we see. So to recap, we have different problems with the sources of the material with abundance patterns. We also don't see any winds gathering in the center of the clusters. So this means that we don't have any fuel for star formation that is going to create the next generation stars with the phonic chemistry, okay? So this picture is pretty consistent regardless if you look for molecular gas, H1, dust emission, or dust absorption. So the next point now might seem a little bit trivial, but I'm going to go over this quickly. So do we see a new generation of stars forming with the peculiar abundances in the center of these young clusters? So if you think having an even more massive cluster will help you with the gas retention, we see that even in 10 to the 7 to 10 to the 8 solar mass clusters, we don't have any gas within them. And when you derive the star formation history, it is consistent with a single star formation event, a delta in time. So it's not we missed the star formation burst, okay? Remember, the models that we invoke star formation events that last hundreds of millions of years. So if everything is correct with these models, these clusters should be forming stars like crazy, but this is not what we see. Okay, so at this point, you might be thinking, wait a minute, that's all fine, but obviously the massive clusters forming today are not the same as the old globular clusters that form at high redshift, okay? You might also say things were different at early universe, where globular clusters form. Maybe there's something special, a special condition that we're missing that has not been folding into the model. And the other thing is that you haven't even talked about the abundances in these young clusters. You only talk about star formation or gas. And you'd be right, I've ignored that so far. And there have been people that have folded these special conditions into the models, and they've put a lot of work and a lot of effort and come to very detailed models. And so let's see how the evidence stack against this. So here I'm showing you an optical CMD of a young cluster in the LMC, okay? It's 2 gigayears old. This is something very young for us, typically studying things that are 10 to 13 gigayears. Note that in this CMD, the blue and red stars that I highlighted in the red giant branch are mixed together. You can see the distribution here in the inset, in the histograms. They all have, they are not offset to each other. However, when one looks at this exactly the same cluster in the corners that are sensitive to nitrogen variations, the stars clearly split into distinct sequences, just like we see in all the globular clusters. Here's an example. So here you see that the blue stars are preferentially to the left, while the red stars are preferentially to the right. These are stars with these two, with different nitrogen variations, okay? You can see here as well in the histograms, in the inset, that these two distributions are offset to each other. So what's more, given that its young age, we can place a very, very strong constraint on the age difference between these two populations, okay? So basically, you do the same trick that we did in the red giant branch, but now in the soft giant branch. So you can see the relative brightness between the two population stars, the blue and the red, to place a constraint on the relative ages between these two groups. When you do that, you find that they are virtually the same age, okay? Just like we found in the other clusters that I showed you before. They form in an instantaneous single burst. Remember, the models predict that the age difference between them is a few 100 million years, and this is excluded at high confidence with these measurements. So let me go back to the slide with the summary. So these are the main premises of the current models put forward to explain how globular clusters and the peculiar abundance patterns form. The first premise, but this is a product of hot CNO burning. This happens in the interiors of massive stars. However, we have shown that this picture is at least incomplete, and there are some chemical patterns that cannot be reproduced by these means. Second, these models predict that the ejected material by these stars is going to gather in the center of the clusters, okay? But we have seen that this is not happening. We never found the gas reservoir predicted by these models. So this explains why we now don't see any multiple star formation events. And when you measure the age difference between these two populations, we get a delta that is basically 0, okay? So I have shown that they are showstoppers in all of these premises, and the predictions of these models disagree with all kinds of observations. But there is more. So we have now large systematic surveys that have revealed unexpected scaling relations. And these are very cool pieces of evidence, as we don't have any knob in the models that we can tune that can reproduce this kind of behavior. So now I'm going to show you just a few examples. So first, we see, for example, in the top panel, that the degree of nitrogen variations from star to star in a globular cluster scales with the mass of the cluster. Similarly, in the bottom panel, you can see that the number of stars in the cluster showing the phonic chemistry also scales with the cluster mass. We also found recently a scaling relation with age. You may think that this trend might be some sort of evolutionary effect. However, if you ask me later, I can show you more about this. But using unevolved stars in the main sequence, we found the same result, okay? Consistent with this trend. Okay, so now let's regroup. So there are many loose ends in the problem of globular cluster formation and the origin of their abundance anomalies. Essentially, there are problems with the sources of these abundance patterns. then we cannot explain how, without invoking multiple star formation events, how we can get stars with different chemical signatures. We also don't know how these scaling relations came from. And back to the original idea that started all this, how we can use these peculiar abundance patterns in the bigger picture and the bigger context of galaxy formation. So in the next few minutes, I'm going to present very quickly 2 projects that can help us move forward, okay? Both of them have more than enough data in public archives to start the analysis. So the first thing I'm going to focus is on the scaling relations, okay? That we cannot get out of the models that exist so far. Okay, so now I'm just trying to provide a big picture of this phenomenon. Okay, so I'm just going to try to see how this manifests in global clusters of different properties, and if this how robust are these scaling relations. So far, we have done all these studies in global clusters in which we can resolve individual stars. These are the ones very nearby, so basically in our galaxy and in the Magellanic Clouds. But the problem is that nearby globular clusters are not a representative sample. And what's more, we cannot test the scaling relations that we see, for example, in the Milky Way with the Magellanic Cloud clusters. Because, for example, although in the Milky Way we have a wide range of metallicities in globular clusters, they are all very old, so we cannot test the dependence with age. On the other hand, the Magellanic Clouds, we have a wide range of ages, but we cannot test the mass dependence because there are pretty low mass, okay? So to overcome these biases, I'm trying to take a new approach that allows us to study more distant clusters to compile an unbiased sample of clusters to test this phenomenon. Okay, so I'm going to show you now an example of a paper that we're working on right now. What I'm doing is basically using Charlie's code to derive abundances from galaxy spectra to study the abundances for globular cluster stars that cannot be resolved into individual stars. So this is the integrated spectra of a globular cluster. This is the spectra of all the stars together. And by doing these fits with this code, we can derive the age, the metallicity, and the abundances of different elements that we care about. And so far, we have been getting pretty good results. And everything is looking pretty promising. And I think, yeah, soon we're going to be able to test these scaling relations. So how are we going to do this? So the idea here is to compile data from the literature that already exists of clusters with different ages, masses, metallicities, environments, okay? And see how robust the scaling relations that we see in nearby clusters are. So here, for example, I'm showing you a few examples of data that exists already in the literature of clusters at different ages. So here, the idea is just to, for example, at a given age, at 3 gigayears, see if we can find this trend with mass. And then compare it with the same, if we find the same trend at a different age, see if we can see this trend evolving. And so hopefully all this will tell us if we have any missing pieces in the puzzle of global cluster formation. If those scaling laws are universal or if they are unique to the galaxy and Magellanic Cloud clusters. And perhaps we can pin down a critical parameter that allows these peculiar abundance patterns to develop. How will we know about this? It's basically if we, for example, all of a sudden stop seeing the abundance variations after a certain threshold, okay? So the second project that I'm going to focus on is try to put the globular clusters in the bigger picture of a buildup of galaxies. So the properties of globular cluster populations that we see in galaxies not only reflect how they form, but also encode information about their evolution and their disruption. So here, it looks like at least a significant fraction of the stars in the inner galaxy show the chemical patterns similar to those characteristic of globular cluster stars. So here in this plot, you can see, for example, that in the middle panel, we have this population of stars that are very nitrogen rich, just like we see in globular clusters, that make up a lot of fraction of the mass. We're talking about almost 10%. This, if you compare it to the numbers below in the bottom panel, that you see the number of globular clusters in the Milky Way, we can see that there are significantly more than the entire current present population of globular cluster stars, okay, that exist in the galaxy. So even if you put all the globular cluster stars and dissolve them into the field, you need 8 times this mass, okay, to come up with these numbers. So this suggests that there was an initial population of globular clusters that was completely disrupted and now makes up the field. So this is not unique in our galaxy. We have evidence for this as well in Andromeda, where we see strong nitrogen and sodium abundances towards the center of the galaxy. Also in ultra-compact dwarfs, there are objects between galaxies and globular clusters. And also in early type galaxies. So you have this UV upturn that is a signature of helium-enriched populations, just like we see in globular clusters. And we also see nitrogen and sodium enhancement in the very cores of these galaxies. So the idea here is to see if we can trace the number of globular clusters that we see in the center of these galaxies, if we can reconcile them to the abundances that we see in the field in these same regions. So the idea is, so since we're missing a bunch of globular clusters that got disrupted here, and you can see this from the extrapolated radial profile of the globular cluster population, you can see that we're going to try to see if this, we can reconcile it with the abundances that we see in this, of the field stars in these regions. So there is a bunch of data already public to do this. So this is data from Galax that will gave us the information about the UV upturn and the helium-rich population. With HST, we can trace the radial profile of the globular cluster population and see how many are we missing in the center compared with the outskirts. And we have the spectra of the field stars, the integrated spectra from IFU surveys like Khalifa, Timer, and Forest 3D. So with all this, the idea is that to see if we can take advantage of these chemical peculiarities to provide a fresh approach to trace the galaxy assembly. So we're going to quantify how important is the contribution of dissolved globular clusters to the mass budget of these galaxies, how these abundance variations affect the IMF estimates, and if we can take this peculiar, if we can see if we cannot explain it with a normal globular cluster disruption, maybe this is telling us that these globular clusters are forming outside, if these stars with funny chemistry are also forming outside clusters as well, which will bring a new take on the problem of these abundance variations. So let me wrap it up. So we have many loose ends regarding the nucleosynthesis of these abundances, the fact that the stars with different chemical composition are all of the same age. We have these scaling relationships that don't come out from the models that have been proposed so far. And there is a possible connection with galaxies that we can use these peculiar abundances of globular clusters as tracers for the buildup of mass in the very center regions of the galaxies. So all of these loose ends are very important and make it exciting to study the formation of globular clusters. And maybe one day we'll tie those loose ends and make a coherent picture of globular cluster formation. Or maybe it will tell us that we're thinking about the origin of these peculiar abundances in an entirely wrong way, and some big revolution in science is coming. And with this, I think I've finished. So if you have any questions, I'm happy to address them now. That's it.
Thank you very much, Ivan, for that great talk. I think we have a raised hand from Anna. Please remember to unmute your microphone.
Hi, thanks for the great talk, and hi, Ivan, from afar.
Mm-hmm.
So you're saying that the abundances in star clusters, like in the center of galaxies, agree with the abundance in globular clusters, right? So one of the ideas too is how what your talk was about was how do globular clusters form. So could it be that maybe globular clusters are pushed out of their host galaxies, like as an evolutionary thing? And what we're seeing is, like one example could be that you could have multiple phases of star formation in galaxies in a cluster based on gas being funneled and so on.
Yeah, so let me see. I think I have a picture here. Yeah, so you can see that global cluster formation, this is a simulation from a group in Liverpool and Heidelberg. It's pretty crazy. So global clusters don't stay where they form. Some of them just get kicked out by their evolution, right? But however, they still have the input from when they form. Okay. So, and this is what they use to what's the name? To reconstruct these assembly histories. For example, the papers by Dietrich Krausen with the discovery of the Kraken. So they use the chemical decomposition and the ages of the clusters just to derive this. So so basically, some of them are going to be expelled, some of them are going to remain, some of them are going to be dissolved. And so all that is very messy, and you have to find a way to see if this is telling us something about these peculiar abundances that we see in globular clusters.
And I guess along with that too is I know gas is funneled. I don't know too much about stars, so usually you have gravitational instability in the disk that can funnel gas towards the center of galaxies. So I guess, definitely a lot more work has to be done about how if clusters get out of galaxies and so on. More so just for, I guess, understanding. And I don't know if the simulations see that, but there's definitely been a few simulations that looked at mixing and gas being funneled in galaxies due to gravitational torques and all that. So probably doing something with tracers would be interesting. Yeah.
So I think the key issue with this is that we need to explain why we don't see it in the halo globular cluster stars. You see?
Oh yes, yeah. That's true.
Because you see that at a given metallicity, for example, in the very metal Puran, this make a lot of diffraction. In the core of the galaxies, but in the halo we don't see it.
Maybe it could be due to dynamic effects, like halo stars maybe are born in more unbound associations or something, and because like to push a star cluster out to become a halo globular cluster, it has to stay intact. So maybe it's just something different about that.
Yeah, but maybe.
Anyways,
I'm not an expert.
We should talk later.
Yeah, sure.
Yeah. Thanks.
No worries.
We have two raised hands. Sovnak. Sovnak, did you have a question?
Mine was just the applause sign.
Oh, sorry. Did anybody else have a question?
I think Anna might have a question.
I have a question. Yes,
hey, Anna.
so to make sure. Hey, so maybe just to tie in to what like the previous question about the halo, like the population, like contribution of globular clusters to the stellar halo. I think that's expected to be very, very small. So I guess I wouldn't be too surprised that there's not that many like funny chemistries in the halo. But my question was, okay, very sort of empirical. So all of these weird abundances seem to be in the light elements. And this is just kind of noting that now there's been a lot of interest in the R process and the other neutron capture elements. So just wondering, like, are there any efforts to measure the abundances of these like heavier elements in globular clusters? Or, like, could that maybe provide some insights into what's going on?
Yeah. So pretty much the evidence we have comes from the way the surveys have been designed, and they have been designed to study what we already know that they were changing, you know. So there are a few clusters, for example, that were like 2808, where we have pretty much the abundances of any other element, but there are very few clusters that we have studied in that kind of detail. So maybe there are other surprises out there, but I will dare to say that most of them are not going to be changing that much, and this is why we have focused in this very particular set of elements, you know, this hot CNO cycle elements.
Yeah, no, it was kind of out there question, but I guess I guess maybe if there are like bulge surveys for like other reasons, it might be interesting, yeah, to see if there are any correlations or surprises.
Any other questions? All right.
Okay.
Yeah, it doesn't look like we have any more questions. Well, thank you very much, Ivan, for this really interesting talk. And thank you, everybody, for joining us, and see you all next week.
Okay. Bye. Thanks.
Bye.